Hi everyone, this is Analog Circuit Design, Lecture 22, Feedback and Stability. I'm Tae Kang. I'd like to acknowledge my advisor, Michael Flynn, and also Dr. Seung-Jong Lee. Here's the outline. We'll talk about feedback. What is feedback? Here's the very basic example of feedback amplifier. So what is the gain? Gain would be the V out. V out is actually this voltage and this voltage difference times A0, which means A0 times V in minus this voltage, which is voltage divider, R1, R2 V out, right? If you just do some math, it would be V out 1 plus A0 R2, R1 plus R2 is A0 V in. So the gain, voltage gain would be V in over V out, V out over V in, which is A0 1 plus 2 R1 plus R2. So this is the gain actually, and but usually what we assume is A0 is really large here. A0 is really large. So what happened is AV would be if A0 is really large, then it's this one. So which is R2 R1 plus R2 1 plus R2 R1. So this is kind of basic thing. So that's how like we use this amplifier to make certain to kind of amplify the V out, V in to V out, right? By this ratio. So this is one type of feedback. And for feedback system, we can represent the system like this. So first, this one was like amplifier gain, and then beta is like feedback factor. So usually we need big gain. We want big gain. And for feedback factor, usually we want accurate. So for example, in our previous example, here, the A0, that corresponds to this part, right? So this part is amplifier, and the X corresponds to V in, right? In and output Y, so this is V out and then V out, right? Output. And then what is beta? So that one was R2, R1, and so we want to see this part, right? So because here is beta Y, and when we see this point voltage, that's V out times R1 plus R2, R2. So this is beta, right? Well, there's a lot of example. Cruise control. Cruise control is like try to keep the speed same, right? Or thermostats, autopilot, biology, balance. So, I mean, everything is feedback. And also in electric circuit, I mean, in circuit design, we also use a lot of feedback. Then why do we use feedback? There's a lot of reason. They have a lot of advantages. First, desensitized gain. That means that the AS, for example, in analog circuit wise, this is amplifier, right? It's more like we don't really care about amplifier gain, I mean accurate gain. What we want is we just want large gain. So it's a lot better. It's like assuming that we want gain 100, exact 100 versus larger than 100. So the difficulty to achieve this is a lot easier, right? A lot easy to achieve. I mean, achieving like 100 exact gain is really hard. It's almost impossible. Of course, because of the PVT variation. So that's a good part. And then reduce distortion. It's like they can suppress the signal distortion, like when they amplify it. And also we can modify impedances, and then also we can trade off gain for bandwidth. It means that if you want to use this amplifier in this format, we can increase like a bandwidth of this amplifier, but also sacrificing gain. In circuit-wise, in analog circuit-wise, especially in this lecture, this would be a very good example of feedback. We will cover it in the next lecture. So what you can see is here the amplifier, like it's a differential amplifier, single-ended, and then there's another stage. So it's like a two-stage amplifier. So if we just make it as simple as like this. So this is how we can represent this whole circuit as this amplifier. And what we can do by using this circuit is we can make a unit gain buffer, which means V in is V out. What we're doing here is, for example, this is V in, so that goes to the minus. So if we think about the polarity, so here is plus, right? Plus, and then minus, and then this will be plus. And then we have to connect this line to V out to here, the minus. If we connect those two nodes, then and then here is still V out, then we can achieve this unit gain buffer. So that's why we need to learn. This is just one example of feedback, and then that's why we need to learn about feedback in analog circuit design. And the reason why we need like this kind of buffer, it's we can like it actually gives up more drive strength. So that's what buffer means, right? Let's say this input is really weak signal, but we want to drive something really big, then we can use this buffer. Even though the strength of this signal is really weak, this amplifier with this feedback can drive a large load. So it's like here. So there's a lot of application. Also, you also see that like we can also use some resistor thing, so we can make some gain too, right? So anyway, in analog circuit, we use feedback, and then this circuit can be a good example of using feedback. In feedback system, first one we need to look into it is A, the gain is a forward path. AS, S means frequency, so it means frequency dependent. So this would be an example. This amplifier, common source amplifier, is a example of this forward path A. What was the gain? The gain was minus GM1 RD, right? So usually in our analog circuit design, amplifier provides forward path. Forward path AS. And again, this S is J omega at frequency dependent. Next one is this feedback path. The feedback path may be a passive or active circuit. So passive circuit means here. What's the feedback? That's this one. So this one is feedback path. Feedback path, here goes the V out, and then the other, well, let's just say F, and here's the F. in this case, what's the beta? So VF is it's a resistor divider, right? R1 plus R2 and R1, R2 and V out. So the beta in this case is R1 plus R2 over R1. And then in here, the beta, often the gain, the overall gain is 1 over beta. We'll talk about it later in this lecture. And this is also one important feature, can be function of frequency. Usually we hope not, and then in this case, we assume this is not like frequency dependent, which means we are just using here. You see that there's no feedback factor, but of course, if the frequency increases more, and then there must be a parasitic capacitance, so it can be frequency dependent. But in just calculation in our frequency interest, our interest of frequency, then this can be a frequency independent. And the important part of this feedback factor is when we see here, this is like PVT independent. So this is important feature. The beta usually it's PVT independent. So P is process and V is voltage, and then T is temperature. When you see this beta, they're just resistor ratio. So it's like a constant value. If what it says is, let's say R1 is like 50K, and then R2 is, let's say 100K. So that can be 50 plus 150, which is 1 over third, right? So assuming that there's like 10% variation, so R1 becomes 55K, and then R2 becomes 110K. So this ratio is not changing. That's a key point. Yeah. Well, this would be R2. Yeah, I made some typo, R2, and then it's 100. So 2 over 3. And this is also 2 over 3. So the variation of the resistor is an impacting the beta. And then you can also say that what if this R1 changes 10% and R2 changes like 5%? What if they're not aligned? That's a very good point. What people do here is that they make those things very matched. They use the same piece of resistor, they place them really close. So so what happened is R1 and R2 experience the same variation. That's what designer want to do. So that can be like close location, same unit resistor. So it means that when you want to make like 100K, the same unit resistor means that you're using like 10K to make 100K, and then you also use the same 10K to make 50, 100K. So it's like they have a the same resistor, and then they just use multiple of them, like connecting, something like this. So the important point of this beta is that they are PVT independent. Next is loop gain. TS, as I said, S means J omega, which is frequency dependent. So loop gain is the product of the forward path and feedback path. It's simply this gain. So loop gain TS would be beta times AS. A is the gain of this amplifier. So that's a loop gain. Besides, by the way, the X over Y, which is input to output. So this is closed loop gain. So let's see one example like this. We talked about this unit gain buffer, right? What's the loop gain? Loop gain is beta times AS, and then this amplifier has AS. Beta is 1, right? So this is just AS. And what about the closed loop gain? Closed loop gain is, let's just say if you get the voltage gain is 1, right? Because this is unit gain buffer. So and maybe how about this one? So this one R2, R1, AS. Well, the loop gain of this would be R1 plus R2, AS, right? So that's loop gain. And then this figure shows how to measure the loop gain. So it's kind of tricky because we want to measure the loop gain, but actually these are connected. But what we want is we want to disconnect them, but at the same time we want to keep the voltage there. So that's like assuming that this is an amplifier, and then let's say they have a voltage. If it is unit gain buffer or whatever the other, maybe let's say this is like 0.9 volt, and then this can be let me just draw it in other way. So I'm saying is, assuming that this example, and let's say the input is like 0.5 volt and then output is 0.7 volt. When we want to measure loop gain, we want to keep this voltage same, and then somehow to make it to calculate the loop gain. So in this case, what we do is to break the loop. So this will go to, so that's what it shows. Break the loop and then measure it. But this voltage also should be 0.5, right? Because this is amplifier. So both of them are 0.5. Let's just say volt. So when we want to measure loop gain, we are like break the loop. It's like 0.7 volt, and then like giving them a small signal input, but at the same time we need to keep it as 0.5 volt. So that's how we break the loop. So in this figure, this voltage should keep the same input. So it's more, I'll say it's more like AC ground. So this is like AC ground. So apply the VT and then VF, and then the loop gain would be VT and VF. In actual simulation, like let's say in cadence, we do have like SDB component. So what we do in the actual simulation is that we just put some module here, some basing module, and which actually looks like let me just draw it again. Actually, it looks like this, something like here. So it's like it's like cutting the loop, but not actually cutting the loop. So it's like I probe, and with this simulation, we can measure the loop gain. I mean, the long story short, so loop gain is this beta times A, the gain, and then when we measure the loop gain, we need to keep their operating voltage like this, and then apply the like input here, and then see the output, or even in cadence. In cadence, this is like cadence. In cadence, we cut some. So loop is here, right? So loop is here. Loop is here, and then we cut the loop, and then place the iPro component, and then there's like a simulation, like SDB stability simulation. Then they automatically measure the loop gain. Now let's calculate the closed loop transfer function. So here's the E. E means we use E here because this is error. So it's error. That's why we use E, and then this is minus. What we can do is E is X minus beta Y, right? And what is Y? Y is E times A. So if we combine these two equations, E is A Y over A, right? And X plus beta Y. And in this case, oh, it's actually X minus beta. So this will be Y and 1 over A plus beta is X. So our closed loop gain is Y over X. This is just simply output over input, right? So Y over X is 1A plus beta, which is, in other words, it's A, and then 1 plus beta A. So that's a closed loop function. So we got closed loop gain, which is Y over X was A over 1 plus beta A, right? And what happened is, if A is large, which is amp gain is large, the closed loop gain would be 1 over beta. So that's why the overall gain from X to Y is defined by gain of feedback network. So this is good because this is independent of gain A. So it's good because we don't have to care about the exact value of amplifier. Remember, like what we learned from like amplifier, let's say we have this kind of V in, V bias, and then V out, and then this is PMOS. The gain is minus, the gain is minus GM, like RON, ROP, right? So this value, it's really hard to define the exact value. What we want, since we're using this feedback, what we really want is just, we want to make this large. So independent of large, gain A means we just want large gain, large A. I would say just a large gain. So this is a lot better problem to solve. So this is gain. And how does feedback work? Let's use some more concrete number. So assuming the V out is 1. If V out is 1, what's the E error? That's 0.001, right? And then X is 1/10, which is this, right? So it's like a tracking back to guess what's V in. So if E is, it's like E is V in minus X, right? But E is 0.001 plus X is V in actually. So V in would be 0.101, right? What if V out is minus 1? This is the same, right? Similarly, minus 0.1, this is 0, this one. And if V out is 0, then error is 0, X, this is also 0, V in also 0. So it's just like this line, but not exactly like 1/10. So V in should be here 0.101, and then this is minus this one. So when we see the slope will be, it's like this one, right? So that's the slope. But in our intention of the designer of the circuit, our intention is slope, this slope. That's our intention, right? But by using this feedback circuit, we have a like limited gain, so that's why we have this slope. Then what if we increase like 10 to 4? In this case, the slope will be 10.011, 1/10.01. So it's more accurate, right? So it means that if we have better gain, if we have larger gain, our actual circuit operation will go to our intention, our goal. This is our goal, to 10.1. So having large gain is better. And let's briefly cover about benefit of feedback in more detail. Here's some benefits of feedback system, like desensitize gain, reduce distortion, or modify impedances, or trade-off between gain and bandwidth. But in this lecture, we'll cover these three. Anyway, feedback is really important, really useful. Desensitize the gain. We already discussed about it, right? So as we noted earlier, usually A is very large because it's like amplifier, and the V out over V in would go to 1/beta. So overall gain is independent of amplifier gain, so that's the important part, right? So overall gain is independent of amplifier gain. So it doesn't matter if A changes over temperature process apply, well, that's PVT. So when we design some circuit, the requirement of amplifier is like, as I said, it's not like gain is 1000.0, not like this. The requirement would be gain is larger than 1000, which is, well, 60 dB in this case. So that's like the requirement. And also again, feedback factor, beta, is determined by ratio of resistors or capacitors, which is constant, which is independent of PVT, like independent. But I would say not 100% independent, but mostly, because they still do have some variation. But So for example, the beta can be like R2 or R1 plus R2, right? In actual chip design, the way we make resistor is, let's say this is 10k ohm resistor, and then we use multiple parts of this 10k. That's like, here's the input, and then we just connect them through the metal. And this resistor can be like, let's say, poly resistor. And here would be, well, resistor, let's just say A and B. So it's like A, B. So each of them are 10k. In this case, what's the resistance? This is like 40k ohm. Let's say we want 5k. The way how we make is this. We use the same 10k resistor and then connect them like in parallel. And here's the A and B. So this will look like 10k, 10k, and overall this is 5k. So that's how we actually in analog circuit make a resistor like ratio. The point here is that we set the unit resistor. This is like unit resistor, and using this unit resistor we make various resistance, and we can make 40k by connecting 4 unit resistor in series, or we can make 5k k ohm resistance by connecting them parallel. The reason why we use the same unit resistor is that we just want to avoid the PVT variation, because the PVT variation happens depending on its shape of resistor. So that's how we actually implement the resistor ratio. So for example, like another example can be, we want to make, let's say, like, what can be like 30k and then 20k. The one way that we can make a layout is that the 10k resistor, we need 5 of them. 5, right? And let's say here's the A, and this is A. So that the blue is poly, and then let's say the green is metal. This is the input metal, and then we just connect them all in series, right? Connect them series, and here will be ground. So we connect them as ground, and let's say this is like Y. Or let's say this is F. And then the F would be 1, 2, 3 here. So this one would be F. So that's how we actually make the circuit in layout. So this is layout. The next benefit of feedback is we can reduce distortion. When we talk about distortion, it means that distortion caused by amplifier nonlinearity. So distortion is from amplifier. So let's see this amplifier. So this is gain actually, right? The slope is gain, and we want, as I said, we want large gain, right? So we want a steeper slope. But the problem of amplifier is that they are not linear. So when we say linear, that means the V in and out, they are constant. It means that linear amplifier means gain is a constant over input. But that's not true for every amplifier. Every amplifier has their own nonlinearity. But if we use feedback system, the effective gain becomes a constant, so much less distortion. Let's see what it means. So assuming that we want like the same example, beta is 1/10, and the gain is here. So let's say we have this kind of feedback network. So V in and then V out. So if gain is 1000, it was 10 point, this one, right? I guess. I remember the slope, the gain, the closed loop gain. Closed loop gain was 1/10.01. But assuming that it depends on the input level, the gain changes to, let's say, 2000. So in this case, the closed loop gain will be 5. So even though the open loop gain, the amplifier gain changes twice, like variation, which means nonlinearity, but the closed loop gain doesn't change much. So that's what it says. Even though the amplifier gain is changing, and then here maybe V in is like 0.5 volt, and then here is 0.6 volt. So even though the amplifier gain changes over V in input voltage, the closed loop gain, when we make a feedback system using this gain, then the closed loop gain isn't changed much. So that's what it says. We can reduce the distortion from amplifier. So next is a trade-off between gain and bandwidth. So let's see what it means. Assume the amplifier, this one, has one pole at WP. So it's like, if we just plot the bullet plot, it's like this. So gain, we have gain here, and then this is WP at pole. And then what would be the, how does the closed loop transfer function look like? That's what we try to figure out. So what's the bandwidth here? We can just say bandwidth is WP, right? This is what actually happens is this is 3 dB bandwidth. So the gain is actually, because this is bullet plot, but the actual gain will be like this, and then this gap is 3 dB. So this pole is, this is also F, or 3 dB bandwidth. It's like 3 dB. So we say we assume single pole amplifier, which is AS. So we have single pole amplifier here, and then the transfer function looks like this. And what's the overall gain from in to out? So this is closed loop gain. Closed loop gain. That's, we can represent it like this, right? And just substitute this AS to this equation, then we got this. And if we do some math, let's say we just multiply it like A0, 1 minus WP plus beta A0, and then we do some more math, just calculation, then it will look like 1 plus beta A0, and then here's the important part, 1 minus. So this is our new transfer function. With a given this calculation, assuming that the amplifier is a single pole system, this is just assumption, single pole, but it can give us a very great intuition. So with this feedback, the closed loop will make this equation. And then the interesting part is that our pole is changed. So pole of closed loop is W pole F. That's just a feedback, and that's 1 plus A0 beta, and W pole P, which is the original pole. So let's see this bullet plot. This is our AS, which is amplifier, and then this will be WP, right? But if you use if you see the like closed loop, which is this V in, V out. Closed loop gain is V out over V in. We see that the gain is approximately 1 over beta because we assume that A is like A0 large. And then the interesting part is that WPF is increased, and then it just follows this way. So actually you can calculate the gain. So they are actually meet. They meet at the same point, and the gain just decreased like this. So the interesting point is that the gain decreased, right? In an open loop, the gain was A0, but if you use feedback, the gain decreases to 1 over beta, right? But its pole is increased. So this it means that our feedback loop, the system can operate larger bandwidth. So it's like the bandwidth increased. Bandwidth increased. So when I say bandwidth is 3 dB, 3 dB bandwidth increased by 1 plus A by 1 plus beta A0. So that's why we say trade-off between gain and bandwidth. If you want to have larger closed loop gain, then our feedback will be like this. Maybe it's going like this. And that can be a new prime. So if you have larger closed loop gain, then we'll have smaller 3 dB bandwidth. If you have like smaller gain, the closed loop gain, then we can have larger bandwidth. Feedback is really useful, so we use feedback a lot, but feedback is difficult. Making feedback system is difficult. Why? Because of this. This is what makes feedback system difficult. So we have to be careful about stability. So when we talk about stability or instability, what happens when the system is unstable? What happens when a system is in instability, has instability? First thing can happen is oscillation. It's like the voltage is just keep ringing, which is we don't want, and or growing amplitude. It's like diverge. Maybe the amplitude can grow or just diverge. So we don't want it. We don't want it. But not always. Sometimes we want the oscillation. So for example, on unstable system can make an oscillator. I mean, we need oscillator to make a maybe sine wave or clock. But in our analog circuit design, in this lecture, we say the unstable system is not desirable. We don't want them. We can explain instability using this diagram. So we'll look at how we can get instability from this feedback system. So first, assume the input is 0 and the circuit is at the idle state, like XS is 0. But assuming that we just got some perturbation in the input. So it's like look in the time domain and consider some disturbance at the amplifier input. So it's like some perturbation, some disturbance happens, and if this disturbance happens at the input here, then we can also assume that this will just go through this after summation symbol, right? So assume that we have some disturbance at this node. So we have original distortion here, and this will be the second one is this will be amplified by loop gain. So the distortion will happen here. Well, we'll just say here, and this is 2. So the output of this loop gain is, let's say, amplified, and then there's also the input, right? And if their phases are met, then they become like get a bigger signal. So it's getting, well, it's getting bigger because of this addition with the feedback. So and then it goes back to here again, and it's getting bigger and bigger. So in feedback system, if there is a instability, what happens is with a very small disturbance, the voltage at here E, they're just getting larger and larger. So this is instability, and we also call this as positive feedback, which is not good in our case. So how is this positive feedback realized? We need the feedback signal to be in phase with original disturbance. So in phase means aligned. So original was here, let's say, and then feedback was also should be in the same phase, right? And then when we add them up, they will be bigger. So if it adds up, then they're like getting bigger, right? So so this is minus this sign. So this minus sign will cause 180 degree already. So if assuming that there's no phase, then this positive feedback will not happen because we only have 180 degree. But what we want is, as I said, aligned. Aligned means it's like 36 degree. So how does that happen? So usually this amplifier has a phase. So this amplifier, I mean not usually, all the time, amplifier has phase shift. You know, the phase shift, it means delay. And since it is like, I mean, the rule of nature, everything has delay, right? The resistor, capacitance, capacitor, amplifier has delay. That's why if this loop delay becomes 180, and then we have this, so it's like this. So if this is 180 degree, and then we also have minus sign, so 180 degree again. So like 180 plus 180 would be 360. and that's when the positive feedback can happen. But is that the only like condition that can have positive feedback? No. Amplitude. Even if you have like 100, 300, 360 phase shifts, but if our feedback signal is really small, then eventually it will not diverge, it will not oscillate. So what we need is this phase. So we need this phase shift and amplitude, which is larger than 1. Then the positive feedback happens. So to repeat, positive feedback comes from phase through the loop. So this minus sign gives 180 degree, and then each of them can get like phase shift or delay, and then this can be also 180. And then the other and then again the other condition is that the loop gain, this loop gain should be larger than 1. And speaking of phase, here A, and then this amplifier, usually amplifier adds phase. Feedback network adds very little phase because this can be like the resistor network or something. And then we already did a phase plot for some amplifiers like this, right? And we have pole. That's pole. What pole makes the phase shift? So, for example, if there is a pole WP, and then there could be 45, right? And 130, maybe this can be minus 135, and that's like pole 2. So if you have pole, then phase will go down, which means pole makes a delay, because pole is RC, right? So RC make a RC constant. So pole is like RC constant, which is delay, right? So amplifier makes this kind of phase delay, and this is the time delay. It corresponds to time delay. So in summary of the positive feedback in terms of phase, at some frequency, phase of loop gain, and then usually from amplifier, that will be is the phase of this amplifier, and then feedback factor is 180 degree. It's like delay, and then negative sign contributes 180. So if you add up, the total loop phase is 360. But again, for stability depends on loop gain, right? Which should be larger than 1 at 360 degree. So again, stability depends on the loop gain at the frequency when positive feedback occurs. That is when phase of AS beta is minus 80, and when the phase is minus 80. By the way, don't worry about this phase, the polarity. So it's minus 180, so it's like delayed direction. So sometimes I say just 180, but they're the same, 180 minus 180. I just want to say that the phase shift happens in the delaying direction. So minus 180, it's a delaying direction. Okay. So at that point, if the loop gain is larger than 1, and it's bad, it's just the input will just diverge. Stable? No. When they're exactly one, what happens is they just oscillate. We sometimes need it for oscillator, but not this part. When we implement the feedback for amplifying purpose, we don't want this oscillation, so it's not stable. But when the gain is smaller than 1, they're not accumulated. So they're just stay the same to the value that we want. So this would be our goal value. They just settle to that value, and then this is stable. Next, let's talk about phase margin and gain margin. Now let's talk about the concept of phase margin. What was our the discussion? When to make a system stable, we want to say that when at 360 degree, at 360 degree phase shift, the gain, which is well actually loop gain. I'll just say loop gain should be smaller than 1, right? That's our condition. So let's see this Bode plot, the gain plot. So you see that this is a loop gain, right? Loop gain. And loop gain decreases when you meet a pole. So first pole, when you meet this, that will decrease it like 20 dB per decade. And so it's 0. So what does 0 mean? It's like gain is 1, right? So that's this is our like interest. And let's see the phase here. And then in this case, this is a specific case. In this case, this is an example that where WP, the pole 2 is equal to W unit gain frequency, unit loop gain frequency. The unit loop gain frequency means when the frequency that makes the gain equal 1. So this is just coincidentally the pole 2 is equal to unit gain loop frequency. If this is the case, then what happened is the phase at this point is 135, because at this point this is minus 45 degree, because pole makes the phase delayed lagging. So at pole 1 is minus 45 degree, and then at pole 2 this is 135 degree. So what was our condition to make things stable? At 360 the gain should be smaller than 1. So when we see 360, it actually means 180. Why? Because here's AS and here's beta, and in this case we have a minus sign, and this is already 180 degree. So we want to see this is 180 degree. That's what we want to see. So what's the phase here? This is at 1. This is 135. Is this stable? Yes, this is stable. When the phase is 180, the gain would be here. The gain, what's the gain? The gain is the loop gain, beta AS, is smaller than 1. Well, actually a lot smaller than 1. So this is stable. And in this case, we say the phase margin is 180 minus 135, which is 45. So in this example, for this particular example, when the pole 2 is equal to the unit gain frequency, then the phase margin, we say PM, phase margin is 45 degree. And then here's a rule of thumb, like it's not always, and sometimes people they set their own different value, but like rule of thumb, phase margin usually should be like larger than 60. And then why do we talk about margin? Let's say we don't have any margin, and then we don't know what happened if we have PVT variation, right? So this phase, this graph, and then pole can be changing, so they can like move back and forth because of the PVT. So that's why we want margin, right? And then we want margin because PVT will give us some uncertainty. So literally we want some margin to make system stable. Similarly, we have also gain margin. Gain margin means the gain at 180. So at the gain at 180 is like a lot less than 1, right? As I said, this point, the loop gain is 1. And at this point, I don't know, maybe like it's less than 1, right? A lot less than 1. Well, actually, we can calculate it in this exact example because we know that here is minus 40 dB per decade. We know the slope, so we can calculate the gain here. But well, let's just say at this point the gain is a lot smaller than 1. And then that's this gain difference in dB. That's what we call gain margin. So gain margin usually should be more than 10, but I've never seen a circuit specification that asks about gain margin. So we mostly use phase margin, like 60 or 50 or 45. That's what people actually use. Next, we will see how the different feedback factor, beta, impact the phase margin. So let's consider feedback factor that is constant with frequency. In this case, beta will be R1 plus R2 and R2, right? So what we're going to do, and then A is frequency, the function of frequency, and then as I said, S is j omega. So what we're going to do is plot loop gain in frequency domain and look at the phase margin, which means at gain is 1, right? So that's what we're going to do, and then see how the beta will change the phase margin. So in the system, in the feedback system, and then we discussed about this loop, right? So the phase should be minus 180, and then the gain, the beta A, and it should be smaller than 1, right? That's what we discussed. So we need to see, we can look at the frequency response, frequency graph of this beta A omega. So beta is here again, R2. That's smaller than 1, right? So if we multiply beta to this gain, then it's decreasing, right? Because this y-axis is gain. So the gain decreases and the pole, this pole will stay the same. Why? We assume that the beta doesn't have any frequency dependency. So pole stay the same since beta is freq independent, right? So when we see this graph, the phase margin in before beta, phase margin is where we see this part, right? Before beta. In this case, they're almost 180 already at 0, so phase margin is kind of no phase margin there. But if we multiply beta here, then the gain is just decreased, and the phase, when we see the phase margin, that will be here, right? When the gain, so this part is when beta a omega or s whatever is 1. So this is phase margin. This is phase margin. So it shows that small beta helps instability, helps stable system. That's like what happened is loop gain smaller, and which means that WU is a unit loop gain frequency is smaller, right? Because and here, so this is WU unit gain, like open. Well, I would just say just A. But this one, that one will be W unit gain loop. So it becomes smaller. So unit gain frequency is smaller. However, while pole stay same, why? Beta is not the function of frequency. So hence, phase margin improves. So, and then this is a very natural, I mean, it's very intuitive. We can understand it because when we discuss about how the instability happens, is that the signal is come back and then add it up, right? The signal comes back and add it up. But if beta is smaller than 1, that means they reduce the magnitude of this returning signal. Of course, the returning signal gets smaller, then it's unlikely, the less likely be unstable, right? Because some adding signal is smaller. Then what's the worst case of the beta? I mean, in terms of phase margin, unity gain, because typically we use beta smaller than 1. So the worst case is 1, and this is a unity gain feedback. This is buffer. We use it a lot. So this is the worst case in terms of feedback. I mean phase margin. So in this example, since beta is 1, the open the loop gain and then just amplifier gain are the same here. So here, what is the phase margin? It's like 180, right? So phase margin in this example, the phase margin is 0, which is not good. We need to change the design of this amplifier. Now let's discuss about pole versus beta. But here assume a single pole amplifier. So look at the single pole amplifier with a constant beta feedback. So with this feedback system, the overall transfer function looks like this, right? And then we calculated in previous slides when we talked about benefit of feedback. So in this case, what happened is, so this graph is closed loop gain, right? This graph is closed loop gain, and the gain will be 1 over beta. When we say gain, it means that DC gain, okay? So this is loop gain, beta A0 is loop gain, and then 1 over beta is closed loop gain, which is y over x, right? So that's 1 over beta, and let's say we have pole here. So because we assume that the beta, the feedback, this feedback beta is independent with frequency, so they're just a constant. So the pole, the location isn't changed, right? When from here to here, there's no pole change. So from here to here, no pole change. When we do a closed loop, we calculated, right? Our pole increased. So this would be our new pole. This would be our new pole. And then the new pole is increased by 1 plus beta A0 WP. So here, there's also kind of a trade-off. That means that smaller beta is more stable, right? In the previous slide, we talked about this. But lower closed loop pole, it means the lower closed loop pole means lower bandwidth. Let me just say bandwidth. Why? Like here, if we have smaller beta, we have less smaller WPF, because this is bandwidth. Well, 3 dB. So there's a trade-off. So here we just repeat the equation that we done before. If we assume that single pole amplifier, then our closed loop gain will look like this, and then this would be our new pole, right? Feedback pole. And this would be low frequency, low freq gain of closed loop, right? So what it shows is that the beta, when the feedback changes the bandwidth of this overall system. We can also draw in a pole zero plot. So here, this is like a amp pole, and this is, oh, let me just use different color. This is closed loop pole, and they increase by this amount in the feedback system. So it says if beta increase, the pole will go farther away, and then pole is increased by this amount, or as I said. Now let's discuss about multiple pole amplifiers, because in single pole amplifier, well, actually they cannot be unstable. Only multi-pole amplifier can be unstable, but still what we learned in this effect of different beta values is helping us in analyzing the multiple amplifiers in terms of stability. Here's an example of multiple amplifiers. In this example, what we assume is that this WP2 is, so in this example, WP2 is equal to WU, that's a unique gain frequency. I'll say loop. So in this case, what happened is when in our pole 2, the phase is minus 135. So our phase margin is 45 degree, right? And depends on the phase margin, there's something happen. So it's like, for example, low phase margin that happen, that give us expect ringing. Let me just write it down again. Expect ringing. In time domain, and also picking in frequency domain, because it kind of makes sense, like intuitively, when we have no phase margin, then oscillation happens, right? So if our phase margin is really low, what happens is ringing. So picking a frequency domain, it means like this. So it's like something like this. So that's what happens. From this slide, we want to our purpose of this is that we want to calculate goal. Let's say goal. Our goal from few slides is calculate picking in frequency domain. And our example that we're going to use is a phase margin is 45. It means that our second pole is second pole is a unit gain frequency. So that means loop gain is 1. So which means beta and A omega U loop is 1. Well, in this case, this omega U loop is WP2. Only in this example. Only in this example, since phase margin is 45. So, and the phase of beta A omega U loop is minus 138. What happens is that this, it's just complex number is minus j omega j this 135 degree. So let's just follow the calculation here, and then we have this. So this is a gain, right? This is a closed loop gain, and when as I said, the goal is calculate picking in frequency domain. Use frequency domain closed loop gain. Closed to I mean it can be confusing. Closed loop gain means from V in to V out in feedback system. Okay, so if you let's just do a calculation here. This will be a loop and 1 plus EJ minus 135, and it turns out 3 minus 0.7 7 and a j omega u loop. So this is our goal. Then we can use some little trick, which is a u loop is actually just do some trick. Well, I mean, just a math, right? Because I mean, if we just put it inside, then it's there the same. But what we got is this one is 1, right? That's 1. So this is 1 over beta. So our goal is to try to find the picking, which is V out in terms of magnitude. This will be 1 over beta 3 minus 7, and then it turns out to 1.3. So far what we've done was to try to find this value, which is in this dotted plot. So this is this one. Let me just say in red. So this line is closed loop gain, right? Means here A, beta, V in, V out, and a closed loop gain is V in over V out, and S, right? So that line. So, and then this frequency is loop, okay? And then let's see what it means. It's 1 over, this is a 1.3 over beta. It actually means that the actual graph will just follow here, but at this point we have some peaking. Why? Because this is not 1 over beta, so this is 1.3 beta. I mean, of course, this is like 20 dB scale. This is dB scale, so we have to put all dB around it, but just in case. So what I mean is, this pig is actually 20 low, but you see what I mean, right? So the point here is that when we use a feedback system at this point in a closed loop gain, this one closed loop gain, there is a peaking about this amount. So it's not 1 over beta. They have some peaking, which is 1 over 3, 1.3 beta. So it's like we can say that they have peaking by 1.3. So why does that peaking matter? Here I just brought some image that depends on the phase margin, how many peaking they have. Let's see, what we calculate was 45, right? This one is 45. Okay. This one is 45, and then we got some peaking, right? This peaking. We can actually calculate it. So that peaking is, this goes to 1.3 beta, right? So it's like if you just put log to change it to the dB scale, then it will be plus 20 log 1.3. This will be, so that's what it is, right? Because in the log, then we just multiply, and this value is actually like 2.2728 dB. So this is like 2.28 dB peaking. And also if we have phase margin, so these are like a step response. What step response means, let's say we have some, I mean, I just draw this multiple times. So in this closed loop system, and V out and V in. Step response means if you apply a step voltage here. If you apply step voltage here, and we'll see output, right? Output also will look like this somehow with some gain, which is let's say if this is 1, then this will be 1 over beta, right? But it's not exactly like this step. They have some delay, of course, and then that's what this phase margin talks about. It can be like this, or it can be like this, or it can be like a little bit peaking. That's what it says. When we apply a step function into this system, if you have large phase margin, it just gradually goes to its value, I mean the final value. If you have a little less phase margin, we have a little bit of this peaking, and then if you have like 45, we have some ringing. So that's why in a previous slide, what we said is rule of thumb. Phase margin is like 60. So this is like a good thing. But the other thing that we can think about is large phase margin good always? No. If you have large phase margin, it's slow. So this is faster. So this is faster. So it means that if we have too much phase margin, then it can be slow. I mean, the step function is slow. It means that the reaction of this system is slow. If you have a little bit less phase margin, then we got some, even though we have ringing, we have faster response. So there's trade-off. It depends on the application. Some people want to set, it depends on the application. Some people want to set the phase margin large because they don't care about this slow response. But in some other application, we don't want this slow response. We want some fast step response. Then we set the phase margin like 60, and then it's like a decent reaction time. So here's the end of today's lecture. The reason why we talk multiple things about feedback is we use feedback a lot. And one example would be this unit gain buffer. This out, this unit gain buffer, this is widely used. And then in terms of circuit, let's say we can have like a single-ended amplifier with a two-stage. And so here's a V in. Let's see. Well, this. So let's say this is V out, and then this we can just connect it to this, and then this is V in. So actually, this looks complicated circuit is this one, this unit gain buffer. And since this is two-pole system, multiple system, it can be unstable. So to make this circuit stable, we need to do something to compensate that stability. But we'll cover it in the next lecture. So that's why we just talked about a lot about this feedback, and also the feedback factor. In this case, feedback factor of beta is 1, and the beta is usually smaller than 1, and the closed loop gain, the overall closed loop gain is 1 over beta, right? This is closed loop gain. And we also briefly cover about the peaking with the phase margin. So the message up here is that phase margin cannot be too large, cannot be too small, and it depends on the application.